All right, so let's go ahead and see with an example why we actually would want to convert to polar coordinates and why this is beneficial to us. So we're asked here to convert to polar coordinates and evaluate this integral. So the integral from 0 to 1 of the integral from 0 to root of 1 minus x squared of e to the x squared plus y squared dy dx. So we are given this information, we're given this integral in rectangular coordinates, rectangular. And so the inequalities that we have are from 0 is less than or equal to x is less than or equal to 1, and 0 is less than or equal to y is less than or equal to the root of 1 minus x squared. So if we draw this region, here, so if 0 is less than or equal to x is less than or equal to 1 on our x-axis, we've got this interval. And this we recognize as the top half of a circle, right? This, if we let y equal to that root 1 minus x squared and squared both sides, y squared is 1 minus x squared, bring the x squared over, x squared plus y squared is equal to 1, right? We've got the top half because that is the positive root. So we've got that part here. We've only got from x from 0 to 1. So the region D that we're looking for is this part of a circle right here. And regardless of what the function is, we're going to see with this function there is a particular advantage to using polar coordinates. But for any region like this that is circular, that is part of a circle, we've seen in polar coordinates circles simplify, are very, very simple in polar coordinates. So we can imagine, if we were to imagine integrating this thing here, right, with these bounds, and you would have to integrate and then plug in those bounds, you can imagine having to do some integral with a root sign like that, which might need a trig sub, so already sounding horrendous. And then if we actually look at the function that's involved, this guy. I've mentioned this before. Those that e to the x squared is one of the non-integrable functions in terms of primary transcendental functions. You can do it with a series, but in terms of functions with nice, clean, elementary transcendental functions, there is no integral of a function e to the x squared. So right away, right, we've got all sorts of reasons here. Circular region, we see this nasty square root, we see this e to the x squared to try and convert to something which is going to be easier. So let's go into this region first of all and re-express that region in terms of what we were told above. We need to express that in terms of these inequalities. So we're looking to always, we want to base theta first, theta between constants and the radius between functions. So theta between constants, theta is going from here to here, right? There is theta. So theta is 0. I can write this here. So 0 is less than or equal to theta is less than or equal to, and that is a right angle, pi over 2. And then the question is, where does the radius go? What is the inner radius and the outer radius? Well, the inner radius, we would imagine, right, there is no kind of inner curve. The inner radius would be 0. 0 is less than or equal to r is less than or equal to. And what is the outer radius? Well, the outer radius, here, there's our outer radius. Our outer radius is this circle. That is our outer radius, and in terms of polar coordinates, that can be described as r is equal to 1. So already so amazing. We have a complicated integral up here, right? Complicated bounds, at least in terms of the y component, that have been replaced by constants, simple constants, right? Beautiful, simple constant integrals here. So already one simplification. So we know that our double integral is going to be now always theta on the outside, always theta on the outside. So 0 to pi over 2 of 0 to 1 of e to the, and then we have to look on the inside, right? X squared plus y squared, x squared plus y squared. We could either, we could go into our formulas. X is our cos theta, y is our sine theta, and plug those in and simplify. But it's so much easier just to say that we've got this third formula, x squared plus y squared is equal to r squared. So e to the r squared, and then it's not dr d theta. Remember, we have this gift. We have this gift of the gods, r dr d theta. So r dr d theta. And now we look at that integral, and suddenly, which was unintegrable in terms of clean functions, is now just a u substitution. The bounds, which were horrendous, moderately, before, are now just constants. And so this integral has become, gone from messy, if not impossible, to clean and simple. And all we need to do is a simple u substitution, right? So we're going to use the fact that we'd seen. We've got an integral here with respect to r, and an integral which is with respect to theta. This integral here entirely with respect to r is a constant, and so I can think of bringing that out. So I'm going to evaluate this in two steps. This is the integral from 0 to pi over 2 of d theta times the integral from 0 to 1 of e to the r squared times r dr. That integral on the first bit here, integral of d theta, is just theta. We're going to run that from 0 to pi over 2 times, and then for this integral, let's do just a little u substitution. So let's let u be r squared, so that du is 2r dr. And what do you know? R dr is sitting right there in our integral for us. And so we're going to have 1/2 du is r dr. So this is going to give us 1/2 times the integral of e r squared is u, r dr is du, and then we have to change our bounds. When r is 0, 0 squared is still 0, and when r is 1, r squared is still 1. So that's quite lovely. Well, factor out the 1/2. 1/2 goes in front. The first integral, evaluate at the top minus evaluate at the bottom, times, and now I have an antiderivative here, which is going to be e to the u. Nice simple antiderivative from 0 to 1 as well. Let's evaluate this. So 1/2, the first bracket just gives me pi over 2. The second bracket gives me e to the 1 minus e to the 0. So if we calculate this and clean it up a little bit, pi times e minus 1 over 4. Nice, simple, beautiful integral to evaluate from something that was horrible before.